Omkar, you are the host now. You can start now.
Yes, sir. Yeah. Is my screen visible to everyone?
Yes.
Okay. And I am audible as well, right?
Yes, sir.
Yeah. Did you guys go through the questions that were posted on the Google Classroom?
Yes, sir.
Okay. Right. So let us start discussing those questions. So what about the first one? Was any one of you able to do it?
Sir, this is, I think we've discussed these problems in the class. Unless there is some modification to the question that I'm missing. This is the knapsack problem, right?
Yeah. So knapsack you have discussed in class.
Yes, sir.
What about LCS?
That too, we've discussed.
Okay, that's great. So then what about question 3? Were you able to solve question number 3?
That too, we have discussed in class.
So, okay. So how did you go about doing question number 3?
We prepared an array. Okay, firstly, we took this. Okay, just a second. Oh, okay. I think this is a different question. We've done something where we have some starting times and finishing times for every job, and then we have to pick a selection of them.
Okay. Yeah, that's a little different question. So in question number 3, what we have is a sequence. We have a set of jobs. Let's label them 1 through n. each job has an associated weight and a length. So the weight of a job indicates its priority. So we would, so more the weight, higher is the priority of that job. And the length of the job denotes the time it would take to complete that job. So our objective is to come up with a schedule of these jobs that minimizes a certain objective function. And this objective function is the weighted sum of the completion times. So, well, I need to define what the completion time of a job is. So let us say with respect to a particular schedule or in a given schedule, this is the ordering of the jobs. Then the completion time of the ith job is essentially the time elapsed before the completion of the ith job. So in some sense, it is the sum of the length of the jobs up to and including I in that ordering within the schedule. Okay. And our objective is to sequence the jobs or come up with a schedule that minimizes the weighted sum of the completion times of all the jobs. So objective to find a schedule that minimizes summation WICI as I runs from 1 through n. So is this clear what we are trying to do?
Just once more, can you define CI? CI is the time that has been elapsed till the completion of the ith job.
Right. So it's the
So-
sum of, so
Right.
let's say in a schedule, you have the following sequence of jobs, J1, J2, J3, all the way up to Jn. Then the completion time of J3 will be the length of J1 plus J2 plus J3. Similarly, completion time of J2 will be the length of J1 plus the length of J2. So it is a measure of how much time has passed since the beginning till, I mean, the job gets completed. Make sense?
Yes, sir. And the objective function has to be minimized, right? Right.
Yeah, this is what we are trying to minimize.
Okay.
And we want to come up with a greedy algorithm for this problem. Okay. So, well, what do you think can be your greedy algorithm? So,
Sir, we pick the minimum WILI and then we keep adding the minimum from the rest.
so could you come again? It wasn't clear.
We list all the WILIs and we find the minimum. The minimum becomes the first job, and then and then the next minimum becomes the next job, and that's how we schedule the jobs.
Okay. So you suggest that you basically order the jobs in the increasing order of WI times LI, right?
Yes, sir.
So idea one is to order the jobs in increasing order of WI LI. So does this work? I mean, is it guaranteed to output an optimal schedule for this question?
I think yes, because any other sequence will always be more than in some sense.
So, okay. So do you guys know what greedy algorithm is?
So
Yes.
at every step,
Sorry. Yeah, someone was trying to say something.
so we try to find the solution. So we try to find a solution in a greedy approach. That's a greedy algorithm. We don't. I mean,
Okay, so that's correct. So in a greedy algorithm, you make decisions which are in some sense locally optimal. So you so uh, basically, depending upon what the current situation is and depending upon your options at this point of time, you will choose the one which will best serve my interest. So it is in some sense a very myopic decision that you're carrying out. It's restricted to what situation I am in currently and what are my available options at this point of time and what's going to be of best interest to me in this situation. However, the sequence of decisions that I make throughout the course of the algorithm, they need not necessarily lead me to an optimum solution, right? So that is one of the actually pitfall, you can say in some sense a pitfall of greedy algorithm, that even though you are making locally optimum decisions, the final solution that you get need not necessarily be optimal. Okay. And in fact, this happens quite a lot, that your greedy algorithms need not necessarily yield you optimum solution towards the end, right? That is why, these minimum spanning tree algorithms or shortest path algorithms are quite interesting, because they give you, because they are greedy algorithms which actually give you optimal solutions. However, that need not necessarily be the case. Okay, so whenever you propose a greedy heuristic, you have to also show that it works. That is, it is eventually going to lead you to an optimal solution. And so now, right? So okay, suppose I have this idea and I want to work with this idea. So can anyone maybe try to come up with some sort of a counter example for this situation? So as one of your friends suggested, that this could be a possible greedy heuristic on the basis of which you can order the jobs in the schedule, right? Now, you can either prove that this is correct, or you show that this is not going to work in every situation by providing a counter example for it.
Sir,
Okay.
hello.
Right.
Can I do a slight modification of the algorithm?
Yeah, go ahead.
So we first choose the minimum of WILI, and then from the rest we do W2 L1 plus L. We pick the minimum from L1 plus LIs.
You pick the minimum from
the time that has already elapsed, we add it to the rest of the times, and then the minimum from the WI and the new times. WI times the new times.
Okay. So okay. Right. So okay, so I get your point. So but then again, so what do you think, that will it always work?
Probably.
Okay. So let us try to consider, okay, so let us try to look at this problem first. Let's try to look at some special cases of this problem first. Okay, that might give us some kind of an idea about what might work. Okay, so suppose all the weights are identical. That is, W1 equal to W2 all the way up to Wn. Now, given this, how would you like to order your jobs? Suppose I tell you that each job has the same weight. In this situation, how would you like to order your jobs?
In increasing order of length.
In the increasing order of length. So basically, you would want to schedule the shorter jobs first as opposed to the ones that are longer, relatively longer, right?
Yes.
So we would prefer, so then we would prefer scheduling shorter jobs first. And this actually kind of makes sense intuitively, right? Because if you schedule a very long job first, then all the shorter jobs which will be subsequently scheduled, you are in some sense adding a lot to their completion times due to this long job that you have decided to schedule first, right? So it's always a better idea to get rid of the shorter jobs first so that their completion times are relatively low, and then we can worry about the longer ones. So if all the weights are identical, then we would prefer scheduling shorter jobs first, right? You can, well, actually, okay, we'll talk about it later. Now, so this is first case. Now, suppose all the lengths are identical. That is, L1 is equal to Ln. So each of the job has the same length. In that case, how would you like to order your jobs? Let's say every job has length 1.
So increasing order of W.
No, in decreasing order.
Exactly, it will be
Right,
decreasing order of W, right? Because we would want the job with a shorter completion time to be associated with, well, shorter weight, and jobs with longer completion time to be associated with, sorry, we would want jobs with longer completion times to be associated with shorter weights, right? Because we want to minimize our objective function. So,
Sir, it will be increasing order.
no, it will be in decreasing order, no?
Because it's weight 1 L plus 2
Yeah.
weight 2 L. So we want W2 to be larger than W1.
Pardon me, could you come again?
W1 times L plus W2 times 2L. So since we want W2 to be larger than W1 because it's W1 plus 2 times W2. Oh, we are minimizing that.
We want to minimize, right? Okay, so then we would prefer jobs with larger weights. Okay, and it also kind of fits with what we are trying to do, right? Because each weight is essentially a priority of that job, and we want to and of course we want to schedule jobs with higher priority. We would want to schedule jobs with higher priority first. Okay, so this
Yes.
makes sense.
So this observation actually contradicts the first two algorithms, because we shouldn't then be choosing the minimum of W1 L1,
Right.
because if
Okay.
L1s are all LIs are all equal, then that's the same as choosing the minimum of W1 first, WIs
Right,
first.
right. Yes. Okay. Yeah. So now these are two special cases of the problem that we have seen. Now, what we want to do is we want to combine these cases, because obviously in a general instance of the above problem, we won't be necessarily dealing with these special cases, right? It might so happen that, well, a higher priority job might have more length, might have a larger length than maybe a lower priority job with lower length. So these, in this case, we have a conflict and we would want to resolve such kinds of conflicts. Okay, so, but these ideas can be used to, okay, so what we want to do is the following. We want, using 1 and 2, we want to come up with, let us say, a scoring function that helps us with our decision. Okay, what do we mean by that is, so we want to come up with some function with the property that, okay, please excuse me for a moment. Yeah, am I audible?
Yes, sir.
Okay, sorry for the interruption. Yeah, so what we want to do is, combining the first two observations, we want to come up with some function which will assign a score to each job. And then using these scores, we should be able to decide in which order we want to execute the jobs, right? So using 1 and 2, we want to come up with a scoring function that helps with our decision. So till this point, is everything clear to everyone?
Yes, sir.
Okay. Now, so what are the, so, okay. So now let us define f of j equal to wj by lj. Okay, where j is a job, and fj assigns a score, or fj is the score assigned to j. Okay, we have defined this to be the function with which we'll be assigning scores to each job. Okay, and now our algorithm will simply do the following. It will order the jobs in the decreasing order of their scores. Okay, so the order the jobs in decreasing of their scores. So is this clear to everyone?
Yes, sir.
Now, I hope that why this intuitively makes sense from 1 and 2 is clear. See, if the weights are the same, then we want shorter jobs to be scheduled first. So this scoring function, since it's inversely proportional to the length of the job, it will be scheduling shorter jobs first. right, should the weights be the same. Similarly, if each job has the same length, then we would want higher priority jobs to be scheduled first, which is precisely what will happen should we use this scoring function. Okay, because it's directly proportional to the weight of the job. So should the lengths of the jobs be same, higher priority jobs or jobs with higher weights would be scheduled first. So certainly this scoring function fits quite well with our intuition. Okay, and what we are saying is we'll be, so in the most general instances, we'll be using this function to calculate the score associated with each job and then order the jobs in the decreasing order of their scores, or schedule the jobs in the decreasing order of their scores. Okay, and that will be the final output. So this is essentially your algorithm. Now there are several questions that you might ask, but the first question is that why is this correct? Okay, so as I said, that greedy algorithms, they make decisions that are locally optimal, but you need to show that that eventually the final solution that you get is indeed optimal. Okay, is indeed the global optimum for the objective function that you are trying to minimize or maximize. Okay, so we need to explicitly show how to prove its correctness. We need a proof of correctness.
Sir, suppose we are able to prove that the job with the maximum score has to be placed first. And by a proof of correctness of this algorithm, we will have to prove that eventually. Like that will be proven implicitly. That the maximum...
So you can go about with the proof in a number of ways. So what you're saying is, I think, probably an inductive argument.
So actually, I'm not trying to give a proof. I'm just trying to, I'm wondering about a certain a thing in this algorithm that could probably lead to a contradiction to this ever being able to be proven correctly. So I was saying that suppose that there exists a proof of correctness for this. That means that implicitly we will prove that the job with the maximum score has to be performed first. Then the rest of the jobs, in the rest of the jobs, we can just think of them as our initial setup. But now the times that we will take for every single job will be their lengths plus the length of the time that has already been taken, right? So now the scores we can essentially update to Wi by Li plus that Li star, where I star was the first job.
But if you're observing the rest of them as an independent instance, then that, I mean, that should not really depend upon what has already passed, right? That will be something, I mean, independent of what you have already shown in the previous step.
So, but then isn't the weighted function, the optimization function that we're looking at, isn't that a bit modified now? Isn't Ci now just replaced by Ci plus Li star?
In the context that you're talking about,
right?
Yeah, I mean, for the rest of the jobs, of course, you'll have to add the length of the first job that you have scheduled to get the individual completion times. Yeah, that will be there.
So if we can just replace the completion time of every single job, or the length of time it takes for every single job, by Li plus Li star, let's suppose, okay, I'm not exactly sure whether this step is complete, but
I think I can give an answer to that. If W3 by L3 is greater than W2 by L2 and greater than W1 by L1, then W3 by L3 plus L1 will be greater than W2 by L2 plus L1. And then you can inductively do that for the rest of it.
But then,
Yeah,
okay.
that implies the original ordering is preserved. When
Right. But then we'll have to prove this claim, right? Is it really true?
It's easy. It's just you add the.
Okay.
Yeah.
Okay.
So, yeah, you might want to take a look at it.
Okay.
Yeah. So, in order to prove its correctness, okay, so we'll use contradiction to prove its correctness. Okay. So, let us first of all fix a certain instance of this problem. So, fix an instance of the above problem. Right. Now, suppose sigma is the schedule output by our greedy algorithm. By the greedy algorithm. And let us say sigma star is the optimum schedule. Okay. Now, since we are proving by contradiction, it should be the case that sigma is not equal to sigma star. Okay, because if sigma is equal to sigma star, then there is nothing really to prove. So suppose sigma is not equal to sigma star. Now, so now just for the sake of convenience, what we'll do is we'll rename the jobs in the order based on the order in which they are scheduled in sigma. So to be more precise, we'll rename the jobs to be 1 up to n, such that W1 by L1 is less than W2 by L2, greater than W3 by L3, and so on. Okay. We'll also make an assumption over here that these ratios are all distinct. Assume Wi by Li is distinct. Okay. So here we have simply renamed the jobs based on the order in which they appear in the schedule sigma, and they should satisfy this particular property. So obviously, if they are scheduled in this order in sigma, then by our algorithm, this property definitely holds. Okay. Right? Clear? There is nothing very technical over here that I have done. I have just renamed the jobs based on the order in which they appear in the schedule sigma.
Yes.
Make sense? Right. Now, first, note, or rather note, not note, observe that sigma star must contain a pair of consecutive jobs. Let's denote them I and J, such that I is bigger than J in sigma star. Okay, so it's not necessary to write this. Does everyone agree with this?
Yes.
Yes.
Because if not, because the only schedule in which the jobs are ordered 1, 2, 3 all the way up to n must be our greedy schedule, isn't it? Since sigma star is different from sigma, in sigma star you must have a pair of jobs which are executed consecutively, but the index of the first job is more than the index of the second one. Make sense?
Yes.
To everyone, is it clear?
Yes, sir.
All right. Now we'll do the following. So this is our schedule, sigma star. This is the job I, this is job J. There are a couple of jobs here, some jobs here. Okay. Now what we'll do is we'll exchange the order of the jobs I and J in sigma star. Exchange I and J in sigma star. And let us denote the resulting schedule by sigma dash. So you'll have a couple of jobs here. Now, instead of I, you'll have J first, followed by I, and then a couple of jobs.
So sigma star is the true optimum scheduling, right?
Right. So sigma star is the true optimum schedule, and sigma dash is the one obtained by exchanging the order of the jobs I and J in sigma star.
Okay, so
Right?
it must have higher or lower value of the optimization function.
So let's see what will happen. Now, let's consider different cases. So what we are trying to do is, now after carrying out this exchange, what's going to happen to the completion time of all the jobs? Let's try to see that. So consider a job, K. Now, if K not equal to I comma J, then what can you say about the completion time of K in sigma and sigma star? Sigma star and sigma dash. Will it be
equal.
same or different?
It will be same.
Does everyone agree with this?
Yes.
Because in the set below, like the set before INJ, the completion times are just unaffected.
Right.
And in the set after INJ, we are looking at the completion times. We were just adding up LIs. So instead of LI plus LJ in the last, somewhere in this completion time calculation, instead of LI plus LJ, we'll have LJ plus LI, and the rest of the lengths will be the same order. So we will have the same completion time.
Right. That's correct. Okay. So if at all, just to repeat what he said, if at all your job K is here, then exchanging the order of I and J has absolutely no effect on the completion time of job K. And if at all your job K is here, then instead of adding Li plus Lj, you are essentially adding Lj plus Li in sigma prime to obtain the completion time of K. And that doesn't really affect the completion time of K, right? Li plus Lj, Lj plus Li, that's one and the same thing. So any job which is not I and J, for those jobs, their completion times remain unaffected. Now, what about the completion time of I? Does it go up or does it go down?
Goes up.
It goes up. And by what amount does it go up?
LJ.
Right. Does everyone agree with this? Yes, no? Hello?
Yes.
Is it clear for everyone? See, what we have done is we have exchange the order of I and J. So now I has to wait for J to complete its execution in sigma prime. No, in sigma star, I didn't really have to wait for J to complete its execution. But now, since in sigma star we have sigma prime, we have exchanged the order of the jobs I and J. Now I must wait for J to complete its execution before it could start. So we are adding a factor of Lj to the completion time of the job I. Right? So Ci will go up by an amount Lj in sigma prime. What about the completion time of J in sigma prime?
Goes down by Ci, goes down by Li.
Correct. Okay. Again, this is a result of the exchange that we have done. So in sigma star, J would have to wait for I to finish its execution. But now, after exchanging their orders, in sigma prime, J need not have to wait for I since it's scheduled before it. So Cj, the completion time of J, goes down by an amount Li in sigma prime. So what is the net effect on the completion time? So net effect on, rather, the weighted sum of completion times. Net effect on by carrying out this exchange the completion time of I goes up by Li. So you add up this, add up this constant Wilj, and the completion time of Cj goes down by Li. So you decrease the constant Wj Li from this weighted sum of the completion times, right?
Yes, sir.
Now, can you tell me, so this is the net addition that we get. Now, can you tell me, is this quantity positive or negative?
So we can take Li times Lj common out of this. And then we'll see, we'll have Wi by Li minus Wj by Lj. And we know that Wi by Li is greater.
Right. So this is less than 0, right? Remember, we are ordering the jobs in the decreasing order of their weights. Sorry, not weights, the ratios.
Oh, okay.
So this
right.
quantity is less than 0. So
Yes,
haven't we obtained a contradiction?
Right, because we are able to reduce the optimal function
A contradiction.
from the optimum solution.
So this exchange improvised the well, let's say improvised, or is an improvisation over sigma star. Over sigma star, a contradiction. So that completes the proof. Okay. So the whole point behind actually doing this proof of correctness was to illustrate this idea of exchange. Okay. This is quite often known as the exchange trick. And it is very frequently used when it comes to proving correctness of greedy algorithms. Okay. So is the idea clear to everyone? What we did?
Yes.
Okay, so we started with this assumption And then using this exchange trick, we were able to construct a schedule which was an improvisation over the optimum schedule, which would be a contradiction because this is the optimum. Okay, so that led us to this contradiction, and hence we were able to claim that this algorithm indeed works. Makes sense to everyone?
Yes, sir.
What about the rest?
Yes.
Yes, sir.
Okay. Right. Now of course, one might also ask, how did you come up with this heuristic? Because this need not necessarily be the only heuristic that encapsulates this intuition that we started off with. Okay, so this is where actually, this is why, greedy algorithms are relatively tricky to design, because you might have several heuristics, you might have several possible heuristics on the basis of which you can, schedule the jobs. But then not all might work. Okay, so typically what would you want to do is you might want to come up with several heuristics that might encapsulate your intuition, and then start ruling out one after the other until you are left with the one which you possibly think might work. Again, that possibly thing might work needs to be then formalized through a proof of correctness. Okay, so
if we take wi square, wj square by lj square as one of the possible heuristics that we are we are taking minim of, then we have to prove it, because from that also, from the intuition, the two intuitions that we have, the thing works, because
yeah,
so we have to
yes,
check all these.
you might have also taken wj minus lj. Even that, I think, fits the intuition that we were talking about.
So they could be multiple solutions.
Yes, there could be multiple. So that is actually the whole point, that you can come up with multiple heuristics, but then not all of them will produce an optimum schedule. So you need to start ruling them out by then proposing counter examples, and then you start ruling them out. Okay. Right. Now there is one thing that I want you guys to think about, is this assumption. Okay, we had assumed over here that all these ratios are distinct, but that need not necessarily be the case. So I want you to think about how will you handle the ties. Okay, that is something that you might take it as a homework. Okay, so I'll just write over here. How would you handle ties? All right.
Sir?
Yeah.
Sir, I just wanted to comment on one of the doubts, which was if you were to just take away the maximum wi by li, let's say wi star by li star is the maximum, and then we were just to add li star to the lengths for the rest of the jobs, then that will be an equivalent problem in a recursion sense. But that actually won't be true, because the completion times will be ci plus li star, but then in order to calculate the completion times, we'll be adding li star multiple times. So it wouldn't just be, so if every single job had a length whatever their LJ was plus Li star, then the completion time will have a bigger factor of Li star introduced. So that wouldn't actually be equivalent to finding the
No,
optimum solution.
But then the completion time should include the factor of Li star. No? So
Yes. Sorry.
L1 star is the length of the job that you have scheduled first, right?
Right.
That's what you're saying.
Yes.
So,
so L1 star or Li1, I think Li1 is a better. So Li1 is if we were to just add Li1 to the length of the rest of the times, and then we were to calculate the completion time of, let's say, the third job, that will contain 2 Li1s, right?
Okay, so then then in that case, you won't, once you've added Li to the completion times, then you would have to forget about that first job which you've scheduled. You'll have to think of it in terms of the remaining that you have, because then, as you said, you'll be over counting in some ways.
Right.
Yeah.
So that wouldn't actually work. And also, if WL3 is lesser than WL2 is lesser than WL. Sorry, WILI. So W3L3 is lesser than W2 L2 is lesser than W1 L1. If that is true, then it's not necessary that W3 by L3 plus L1 will be lesser than W2 by L3 plus L2. We can just think of an example where, let's say, W1 was 100 and L1 was 9. So this is the first job that we will schedule. W2 is 4 and L2 is 3. And W3 is 40 and L3 is 31. So we are looking at 4 by 3 and 40 by 31. Here 4 by 3 is greater than 40 by 31. But then in the denominator, if we were to add 9 across both the fractions, then we will have 4 by 12 and 1 exactly. So the order has changed. The relative order actually changes.
Right. Yeah.
So definitely it doesn't make sense that you can just add L1 to all the rest of the jobs, because then that will give us a potentially different ordering altogether. And we've proven that this is the optimal ordering.
Right. Yeah, makes sense. Okay. Now, did you guys try the questions from the problem set? On MST? Yeah.
Oh, from the assignment?
No. MST problem set was uploaded on the course webpage. So you had to try out questions 1, 4, and 5. So were you able to do that?
So I personally mistook it to be from the assignment.
Okay. No, not the assignment, from the problem side. Okay. So okay, let's see. So I actually don't think I'll be able to discuss those questions, and so they aren't really very difficult. If you're able to do, I guess, the first couple of questions from the assignment, then those questions are not really very difficult. You'll be able to do them. So okay, now, so sir, I actually asked me about some questions from the previous problem sets regarding shortest paths and the BFS DFS. So have you guys tried out those questions from the problem sets?
Sorry, sir, could you please repeat? Before the next time?
No, sorry, can you come again?
Sir, could you please repeat what you just said?
So did you guys have a chance to solve the questions in the problem set on shortest paths?
Yes, sir, I guess.
They're provided before the midsem, right?
Yeah, before the midsem.
Yes.
Yes, sir. Yes, sir.
So you were able to solve all of them?
Probably not all of them, but quite a few.
Okay, good. So let's so I think Manas, we did discuss some of the questions from the problem set on shortest paths, right?
Yes, sir.
Okay. Fine. So just give me a minute. Okay, so now consider the following problem. Suppose you are given as input an array A of length n, okay, and you want to find the length of the longest increasing subsequence in this array. Okay, objective to find the length of longest increasing subsequence in A. So, well, how would you go about it with it?
Sir, how much time do we have? Time complexity?
Complexity, well,
We just have to be as efficient.
order n. Yeah, try to make it as efficient as possible. Okay, so let me give you one hint. You might want to use dynamic programming for this.
So, sir, if we were to try to get a recursion of the sort where, let's say, we parameterize our system as B or LIS of J is the longest increasing subsequence in A1 through AJ. And then we want to fill this array of LIS in some dynamic sense. So a recursion for this could be if we want to see whether AJ belongs to LIS of J or not, then we want to see whether
sorry,
so if
AJ belongs to LISJ.
So we want to test whether AJ belongs to LIS of J or not.
Okay. Okay.
So this is how maybe we can think about getting a recursion equation.
Yeah. So well, how would you go about with it then? So suppose you have, so let's consider you have this array A, A1, A2, let's say all the way up to AN.
Sir,
Yeah.
I don't know if I'm correct. So we did try something like this before, right? Because if we just sort this thing and just find the longest common path, longest common subsequence, and that would be the longest increasing subsequence in the A, from the A, then we can just find the length of that.
Right. That would work. Wait a minute. Yeah, that should work. Yeah. That would work. But okay, so leaving that aside, is it possible to directly use dynamic programming on this array?
Sir, we can consider in cross to array where suppose the array is B, then BI0 would denote whether the element is included in that array on the longest subsequence, or DI1 means the flag 0 and 1 denote whether the element is included in that array or not, longest subsequence. And recursively we would go from DI1 to the longest subsequence.
I'm sorry, could you please repeat what is DI0?
So DI0 would be the longest subsequence, length of the longest subsequence till 1 to I, with the element AI not present in that array, longest subsequence.
With AI
not in the
LIS.
longest subsequence.
So, okay.
And DI1, the LIS from 1 to I, where AI belong to the longest subsequence. And at the end we check for the maximum of DN0 TN, 1.
Yeah, but then how will you compute these? That's the whole point, no? Because in order to recurse, you need some sort of a recurrence relation imposed on these as well.
Okay. And
okay, so
sir, this would take a big of n squared. So for each I, we suppose we are interested at first in computing di, 1, whether when the AI is there in that LIS, then for the di, 1, we will see for this maximum of d. We'll check for the element 1 to A1 to AI minus 1, and if if AK is less than AI, then we would consider both the cases, that is DI, 0, DI, 1 plus 1 maximum. And in this way, for each element, we would check for element from 1 to n minus for element AI, we'll check for the element 1 to I minus 1. Then in this way, till we can compute DI, 1, and DI0 would simply require the maximum of the two.
So if I'm not correct, what you're trying to, sorry, if I'm not wrong, what you're trying to say is that you take maximum of DK, comma, something plus 1 whenever AI is bigger than AK. Is this what you're trying to say?
Yes, sir.
Yeah, so do you see that you don't really need this extra index over here? Because this itself is determining whether this is going to be 0 or 1. So,
Sorry, sir. Oh, okay. Got it. Yes.
Right?
Yes, sir.
So, well, you would then basically have to again take a maxima otherwise over here, because you have two possibilities. Your LCS could either contain AK or not.
Yes.
Then you'll have to take a maximum within the maximum. Okay.
The maximum. Okay.
Right. The inner maximum would be within these two. And then for every AK for which this condition is satisfied, you'll have to take the outer maximum.
Yes, sir. So while defining the recursion, we have to write that we are finding the maximum, but while doing so, we are just selecting it. So we don't need to, while selecting, we are making the choice.
Sorry, can you repeat? What were you trying to say?
So, sir, while writing the recursion, we have to mention that we are taking the maximum, right? But while computing, we are making the choice that AI is selected or not. So
see
that choice.
When
I mean, okay, sir. That thing we are also finding the maximum. So it's fine. Yes, sir.
So even while computing, you will need to compute the maximum, no? Because you will be essentially implementing this recurrence relation that you develop. Okay. Okay. So let's so let us yeah.
So wouldn't there be a problem with this algorithm in an array? Like, let's say we take 1, 2, 3, 6, 4, 5. If we were to look at this array, then 1, 2, 3 get appended in our LIS in the D3, and then we include 6, and we don't include 4. And since 5 is greater than 6, we don't include 5 either. So by the end of the 6th step, we would have 1, 2, 3, 6. But the longest increasing subsequence was 1, 2, 3, 4, 5. So there could be a problem, right?
Right. So you just a minute. So 1, 2, 3, 6, 4, 5. So 1, 2, 3, 6. 1, 2, 3, 4, 5. Yeah. So, well, how do you think will we go about with it?
So is there a problem with this algorithm or not? There is, right? Because up till the 5th stage.
See, we are taking the maximum over all those. See, if you consider this element 5, if you look at this element, now for this element, the maximum is over all those longest subsequences where the element is less than 5. So in some sense, what I'm saying is that, okay, so now suppose I have 5. Now, what are the possible subsequences where I can append 5? It'll be exactly those where any subsequence ends in an element which is less than 5. Only then can I append 5 to that longest sequence, no?
Yes, sir.
Makes sense.
Right.
Right. Suppose I have this array. Now 5 can be in any any increasing subsequence that ends in an element less than 5. Only then can I append 5. Now, what are the possible candidates? I can have a subsequence ending in 4. I can have a subsequence ending in 3. I can append 5 to a subsequence ending in 2 or ending in 1. I cannot append 5 to a subsequence ending in 6. So now, if I So I will then be taking the maximum over all of these subsequences. So now any subsequence that ends in 4 will also have 1, 2, 3, 4 as its subsequent, as is in fact from based on this example, a subsequence ending in 4 would be 1, 2, 3, 4. So when 5 gets appended, you get the same answer, no?
Right.
So I think this is over all those k where I mean, it's
Over all
over
those
all of the
subsequences.
choices of k that satisfy this condition. It's
Right.
okay.
Just so that would be for that we would require this all these subsequent somehow access to them, and maybe if we could have them stored already, or something like, okay, if let's define LIS of j, or something like LIS of j comma k. If we could parameterize it as this, where actually it should not be LIS, it should be IS of j comma k, where we define this as the among all those increasing subsequence in A1 through AJ, which has exactly k many elements, such that AK is the smallest. If we can define it this way, then we would have just a list of all those increasing subsequences which are optimal in some sense. They are reducing their maximum.
So, but why do we need 2 parameters? Suppose I have this AN. So as we said, so 5 can be a part of only those subsequences which end in an element smaller than 5. For instance, can be a part of an increasing subsequence ending in 4, in 3, 2, and 1. So if I simply define, so LIS of n, let us say, if this denotes the longest increasing subsequence for longest increasing subsequence for A1 to n, then LIS of n can simply be defined as 1 plus the maximum over all those j's with the property that AJ is less than AN. Right? So here we are outputting the length of the longest increasing subsequence. Does this make sense?
So you're maximizing over J, which means
with this property.
So, but then maximizing over J is just varying over J, right? I mean,
yeah. So when you implement it, you are essentially doing the same thing, right? You iterate over all J's. For whichever J this property is satisfied, you probe at this location and then see what the LIS is at that point.
So but how are we defining A of J?
A of J is the input array.
Oh,
so
okay.
Let's forget about the implementation details. If we forget about implementation details for the time being, is this recurrence clear?
Yes, sir. Makes sense.
What we are doing.
Right.
What about the rest?
Yes, sir.
Is it clear to everyone?
Yes, sir.
Yes, sir.
Okay. So if this is clear to everyone, then now how will you implement it?
We can implement it in ascending order of this array of LIS. We can just figure out LIS1
so
first.
let's say you have an array LIS 1 to n. This will store the lengths of the longest common subsequences. Store the length of the longest common, not longest common subsequence, the longest increasing sequence, my bad. So, right. So I have this array. Now, how do I populate it? Now, first of all, I need some kind of a base case, right?
Sir, actually, there could be a problem with this recursion, right? Because what if AJ is lesser than AN, but LIS of J does not end, sorry, this LIS of J does not include AJ. It ends at some subsequence which has value greater than AJ as well as value greater than AN. Then we can't append AN to
value.
Sir,
right. Yeah.
Because
so see, no. So, okay. So this is not going to be the final output. This is basically just computing the longest increasing sequences ending at each point. After that, of course, you'll have to take the maximum, no?
Oh, okay. So LIS of J computes the longest increasing subsequence which ends at AJ.
Right.
Okay,
so
okay.
Let me actually make this a little more general. I should have. Okay. Maximum overlap. Right. So how would you go about implementing it? So of course, initially everything would be 0. Then you run a loop. So basically you walk through the array, and then for every j for which this condition is satisfied, you use this recurrence.
Yes.
Does this make sense?
Yes, sir.
What about the rest?
Yes, sir.
Okay, so think about it. How would you go about implementing it? Okay, think about the implementation and the time complexity.
So time complexity will be n squared, right? N squared will be because.
Right. Yeah.
So can we do linear? Like anything better than this?
Linear. Even I'll have to think about it. So I'll let you know. But even I'll think about it and let you know. Okay.
So if we just have an ascending order array, wouldn't it just be n squared? I mean, I'm saying the worst. I'm looking at an ascending order array. Then wouldn't it be an n squared algorithm, because we have to check
yeah, so
every single element for
no, but in general for this problem, can you show that you will need an n square algorithm? So with respect to this algorithm, you might need n square, but for any algorithm that solves this problem, can we show that there is an n square lower bound as well?
Oh, okay.
That so I'll think about it, and if I get something, I'll let you know.
Okay.
Okay. Right. Okay. Fine. So I think let us then end today's class. So I hope you try to solve question number 1, 4, and 5 of the problem set. It's posted on the course webpage. If late time permits, we'll discuss the questions later on. So do you guys have any doubts, any questions that you might want to ask? If none, then let us end today's class.
So I
Thank
don't
you,
know
everyone.
if we have discussed the problem number 8 in the shortest path. I don't know if we have discussed.
Problem number 8.
Yes, sir.
Okay, let me see. Let me see.
Sir, I think it was the toughest question of the one where Jordan's algorithm, I think. Something like that.
Sorry.
Sir, I think it was Jordan's algorithm or some other algorithm that we haven't learned. It was just a.
Okay, let me just go through it once. Okay. Right. Okay, let me give you a very high level idea on how to go about with it. Yeah, so are you able to see my screen?
Yes, sir.
Hello. Yeah.
Yes, sir.
So you have been okay. So you have been given a graph G, V, comma, E, and the edge weights are not necessarily positive over here or non-negative. Now, with algorithm whether G contains a negative cycle or not. So how do you determine whether G will contain a negative cycle?
Can you repeat?
See, you are given this graph. The edge weights are not necessarily non-negative, and you need to report the shortest part distances between each pair of vertices, provided G doesn't contain a negative. And if at all it contains a negative
Sir, there
report
seems to
to
be problem with your internet connection. Your voice is getting disconnected.
I'm sorry, am I not able to everyone?
Your voice is getting cut.
Okay. Give me a moment. Is it better now? Hello?
Yes, sir. He says better, I think.
Okay. So you are given this graph as input. The edge weights are not necessarily non-negative, and you're supposed to report the shortest path distances between each pair is in the graph, provided the graph doesn't contain a negative cycle. Okay, and if at all it contains a negative cycle, then you should report so. Is the problem statement clear to everyone?
Yes.
Okay. So my question is, how do you find a negative cycle in a graph? Hello?
I guess we will run a algorithm. Hello?
Yeah, sorry, I couldn't hear. Could you please come again?
Yes, sir. So I guess we can run an algorithm from every vertex. Like if we run Dijkstra, then we will certainly run into some problem if there is a negative cycle. Or some, I mean,
okay, so do you know that Bellman-Ford can be used to detect negative cycles in a graph?
I mean, so yeah, Bellman-Ford, sorry, not Dijkstra.
So Bellman-Ford runs for n iterations. One more iteration of Bellman-Ford will let you know whether G contains a negative cycle or not. Okay, so look it up. Okay, so use Bellman-Ford. Okay, see what will happen when you run an extra iteration of Bellman-Ford. Typically, you run Bellman-Ford for n iterations. What will happen if you run Bellman-Ford for one more iteration? Just look up what will happen. Okay, so Bellman-Ford can be used to detect negative cycles in a graph. So what we do is, so you select an arbitrary vertex. So select an arbitrary vertex of G. Vertex in G. Let's call it S. And run Bellman-Ford from S. Okay. So using Bellman-Ford, you can determine whether the graph will contain a negative cycle or not. Okay. So suppose it does not contain an, okay. Then now remember that Bellman-Ford will compute the shortest path distance from the source S to every vertex of the graph. So let us, so let's remember this. Okay, so run Bellman-Ford from S. If G doesn't contain a negative cycle, then the algorithm computes shortest path distances from S to every vertex in G. Okay, so let's just keep this in mind. Now, okay, now let us say that you have a function h, okay, any arbitrary function from the vertex set V to the set of real numbers. Okay, what we have is you have this graph and we have some function h. We don't know what it is for the time being, but we have some function h hu1, hu2, hu3, and so on and so forth. Okay, now, so we have this function with us. Let's say it is given to us for the time being. So it assigns a real number to each and every vertex of the graph. Now, what we'll do is we'll model into a graph G prime, which would be the same as G, but the only difference is that the weight of each edge in G prime, let's say UV, will be HU plus weight of UV minus H of V. Is this, so do you, so see, we assume that this function H is given to us. What it is that we'll see later, and why do we need it? It will become clear later. But let's just assume for the time being that there is some function that assigns a real number to every vertex of the graph. And using these real numbers, we have reweighted every edge of the graph. And this reweighted graph is what G prime is. Is it clear up to now, up to this point?
Yes.
What I have done? Right. Now, consider any path P in G that goes from S to T. So let us say it is V0.
This is the directed graph.
Yeah. Yes, it's a directed graph. I should have. So the input will be a directed graph. So it's a directed graph. Is it clear? Okay.
Okay.
So now consider a path V1, V2 up to Vt in this original graph G. Okay. And let weight Wp denote its weight in the original graph itself. Now, what will be, now if you consider the same path in this modified graph, reweighted graph G prime, what will be its weight in G prime? By the way, the weight of a path is the sum of the weights on the edges of that path. Okay. So I hope that is clear. So did you understand my question?
Sir, it will be WP plus HS minus HVT.
Exactly. Is this clear to everyone? How come we got this result? It's basically a telescoping sum, no? In what will be the weight of this edge in G prime? It will be HS plus the weight of SV0 minus HV0. The weight of this edge would be HV0 minus the weight of, well, V0, V1 plus the weight of V1 plus so on and so forth. So this gets cancelled out. Okay, these quantities would, no, this will be plus. Yeah, so these quantities would contribute to the weight of the path P in the original graph, and these cancel out except for the first and the last. So this is what you get. Okay, so now, so is this clear to everyone, first of all?
Yes.
Everyone? Okay, now observe then that in G dash, the weight of each path between S and T will change by the same amount. Right? Every path between S and VT, let's call this T. Every path between S and T will change by exactly this amount. Right? This is completely independent of the particular path that we have chosen, right? The amount by which this change is happening.
Yes, sir.
So all the paths between S and T are going to change by the same amount. Okay.
Yes.
So if at all, P is the shortest path between S and T in G, then it will continue to remain the shortest path between S and T in G dash.
Yes.
Right? Because every path between S and T is going to change by the same amount. So any path that was shorter, which was the shortest path between P and T would continue, between S and T would continue to remain the shortest path in G dash as well. Okay. So this implies that the shortest paths are preserved in G dash. Right? Yes, no?
Yes.
Yes, sir.
Yes, sir.
Right. So now in G dash, if only I had non-negative edge weights, then I would be done, right? Simply running Dijkstra's algorithm from every vertex would get me through, right? Yes or no?
Yes.
Okay. Now, so this problem now reduces to how should you choose your function h so that the edge weights on every the edge weights become non-negative for each edge in G dash. How should h be chosen so that the weight of every edge in G dash becomes non-negative? And this is where you use this. Okay, that is, your Bellman-Ford has already computed the shortest path distances. So if you choose h of v to be delta, with this is the length of the shortest path method. Shortest path from S to V. Delta SV for all V, then the edge weights in G dash would be non-negative. Yes or no? Now, is this quantity, can this quantity ever be less than 0?
No, sir.
Why is that?
Because we are
You're looking at the shortest paths, right?
yes, sir.
So if delta SV is bigger than delta SU plus WUV, that means your Bellman-Ford algorithm has actually failed to compute the shortest path from S to V, right? It could have easily rerouted from, it could have easily taken a path from S to U followed by the edge UV. That would have produced a shorter path, no? Isn't it? Well, less than or equal to. Well, no, this must be strictly less than. Did you get it what I'm trying to say over here? See, you have the source vertex S, U, V. Okay. Let's say this is the shortest path. Now, the shortest path from, if the shortest path distance from S to V is less than this distance, then I could have easily taken this distance to obtain, I could have easily taken this path to obtain a much shorter distance to V from S than taking this path. Isn't it?
Yes, sir.
But then that would be a contradiction to the correctness of Bellman-Ford, no?
Right.
So that means with this choice of H, I have ensured that all of my edge weights are non-negative now. Right?
Yes, sir. Right.
So now you simply run Dijkstra from each vertex. Once the edge weights have become non-negative, you run Dijkstra from each vertex. So since the edge weights in G dash are non-negative, run Dijkstra from each vertex. Okay. So that does it. So Dijkstra runs in E log V time and you are running V iterations. So that gives you a V log V algorithm. Okay. So just to summarize, what we have done is you run Bellman-Ford, record the distances from S. This is a very high level sketch that I'm giving you. Then construct G dash by reweighting or reweighing each edge as given above, and then run Dijkstra on G dash from each vertex. Okay. This takes, well, V times time, this will take v log v time. This will take v log v time, and this is just v plus c. So the overall running time will be ve log v. This algorithm,
Bellman-Ford will take v squared time, right?
yeah, it will take ve time. This algorithm is known as Johnson's algorithm. Okay, so if you want, you might look it up. Okay, but this is how it works. Now here we have actually made an assumption that implicitly we have assumed here that G is strongly connected. Okay, implicitly assumed G is strongly connected. But if that were not the case, then you would have to make a slight modification in this algorithm. Okay, which I'll leave you to think. It's a very small modification just in terms of how you pick your arbitrary vertex. So I hope this is clear. If it's not clear, please go through it once. Okay, it's a very interesting algorithm. And one of the advantages of this algorithm is that it proves to be especially useful when it comes to computing all pair shortest paths in sparse graphs. Okay, so take a look at it.
The sparse graph?
Yeah, sparse graphs. It's I think so that for sparse graphs, this is the optimal one. But even I'll have to confirm it once. But I do know that it is definitely useful when it comes to sparse graphs.
Can you just say what a sparse graph is?
Sparse as in the your number of edges is of the order of the number of vertices. So E is of the order of V. Yeah. So any doubts, questions? Did you guys understand what I was saying when it came to this Johnson's algorithm?
Sir,
if you have,
can you just repeat what you said about strongly connected?
I'm sorry, can you come again?
Can you just repeat what you said about the strongly connected graph, like what we needed in Johnson's algorithm?
Yeah. So So in this, the algorithm that I talked about, we implicitly make an assumption that the graph G is strongly connected. Okay, but if at all it's not strongly connected, then you need to make a very minor change. Okay, in terms of how you choose your arbitrary vertex when you run Bellman-Ford. Okay, very small change. It's not a very significant one. What you do is you simply introduce a dummy vertex and add 0 weight edges to every other vertex in the graph. That's it. Nothing more than that. Okay.
Okay.
So
okay.
Yeah. So anything else? It's, I think, already 4 o'clock. So yeah, I think let's end today. End the class today. Thank you, everyone. Hope to see you next time.
Thank you, sir.
Thank you, sir.
Thank you, sir.